right. So this breakfast, and we spoke with Christoph, he told me Large Hadron Collider is a very easy machine from the point of view of the accelerator technology. This is the difficult stuff. And our lecture today about the accelerator technology for the IC is going to be given by Christoph Montag from BNL, and we'll try to understand why this is difficult and exciting from the point of view of the accelerator technology. Over to you.
For the introduction and for the invitation to speak, yes. So yes, I'll give you a very brief idea what the EIC is, how it works, and how we actually collide the beams there. So, this one, so this is what we have at Brookhaven. This is RHIC, the relativistic heavy ion collider. Consists of two superconducting ion storage rings. So the yellow one counterclockwise, the blue ring. This is horrible. Has a circumference of 3.8 kilometers, 6 potential interaction regions, which means in these it has this stupid delay. Okay, so here that's where we actually have detectors in RHIC. This is star, this is S Phoenix, and then here, and here these two rings intersect as well. So we could in principle have detectors in 6 locations there. Beam energies, we have up to 255 GeV for protons or 100 GeV per nucleon for heavy ions, typically gold. 110 bunches per beam, and we have accelerated all kinds of ion species from protons up to uranium. Protons are actually spin polarized. We have reached 60%. I'm always pushing the wrong button here. We have reached 60% proton polarization, so that makes RHIC the world's only polarized proton collider. And just a fun fact, RHIC has exceeded its design luminosity by a factor of 44 and has been in operation since 2001. It's coming to an end now, so at the end of this year, that's it. Then we rip it apart and we build the EIC, or we rebuild it into the EIC. The EIC design concept in a nutshell is very simple. So you take RHIC, right? You take one of the two rings, we take the yellow ring in our case, with all its injectors, ion sources, all the infrastructure, and then we have to make some modifications and upgrades to really convert this into the hadron storage ring of the EIC. The beam parameters in RHIC are already pretty close to what we need for the EIC, with a few exceptions, of course. The number of bunches will be about 10 times more. So we have 110 now. We want to go to 1160. The beam current will be 3 times higher, so the bunch current will be 3 times lower than now, roughly, right? But the beam current will be 3 times higher. It's 1 amp of protons that are circulating there, and the vertical emittance will be smaller. So the beams in RHIC are round in phase space, and we have to make them flat, because electron beams are flat, and that optimizes the luminosity if they both have the same aspect ratio, the same flatness. And then, of course, to make it into an electron-ion collider, we have to add an electron machine. It's an electron storage ring, 5 to 18 GeV, in the same tunnel as the hadron ring. So in the RHIC tunnel, we have to add an injector complex for that. And this energy range here together, this energy range, 5 to 18 GeV together with the up to 275 GeV for the hadron storage ring, gives us this center of mass energy range here of 29 to 141 GeV. I typically speak about protons because ions, there are just too many species and I can't list them all. Protons are the easy ones, and from there one can basically convert everything for the other species. And then, of course, we need to design and build a suitable interaction region where the detector lives and where you actually do your physics. This whole design aims to meet all the goals that are formulated in the EIC white paper, and the particularly challenging ones there are the high luminosity of 10^34 per square centimeter in second, and the high polarization in both the proton and the electron beams. Okay, so the design and performance parameters for the EIC are taken from existing machines. So we take the hadron beam parameters from machines like RIG or Hera, and the electron beam parameters typically from the KEKB factory. So that's a high intensity machine, high luminosity machine. And then, of course, we run simulation studies to confirm that this machine would really work, because all these machines that are listed here, RIG and Hera, or RIG collides only similar species, hadrons with each other. KEKB collides electrons and positrons. Hera was an electron-proton collider, but with much lower luminosity than what we are aiming for. So we are aiming for 2 to 3 orders of magnitude higher luminosity. So it's really a very different beast. So that's why we run simulation studies to confirm that our parameters actually make sense, that the machine would work. And then, of course, we have the advantage that we have RIG sitting in the tunnel, it's running still, and we can test certain things experimentally. So one of the things that we did test is actually the flat beams, the flat hadron beams in RIG. So hadron beams are naturally round. You have to do something to make them flat, keep them flat. What we did is in RIG, we filled both rings, blue and yellow. So that's why we use blue and yellow here as colors in this lower plot. And then we turned on cooling. I will come back to what cooling means later. So we shrunk the vertical phase space of the beam, basically. That's what emittance is, by a factor of 10 or 11. So this here is the ratio. This is the ratio of the emittances in the yellow ring and of the blue ring. So we have achieved here a factor of 8 or 9 in yellow and a factor up to 14 here in this peak in the blue ring. So that is demonstrated. That was breakthrough almost, I would think, because nobody has ever done that, and we really needed to get our luminosity in the EIC to where we want to be. The facility layout. So this is here a cartoon that is drawn at the same angle as this photo here of RIG. So you can identify all the components here. We have the injector complex here. You saw that already in Oleg's talk. So we start here with the proton source, that's the booster AGS, and then we go into the yellow ring here counterclockwise. And then we add the electron ring clockwise. This is actually an older layout, but I still like that because it's drawn at this angle here, and it's nice to identify these things. We will come back to latest layouts of the machine data. So this is the luminosity curve versus center of mass energy. Again, electron, proton. So we have a peak luminosity here of 10 to the 34. That's 10 GeV electrons versus 275 GeV protons. And then when we go higher in center of mass energy, we do that by increasing the electron energy. So when we increase the electron energy, the electrons emit more synchrotron radiation. So we set our limit there for synchrotron radiation to 10 megawatts. So if we increase the energy here, the synchrotron radiation power goes with the fourth power. So we go from 10 GeV electrons to 18 GeV electrons. That's factor 1.8, 1.8 to the fourth power. That's very close to 10. That's why we have to reduce the electron intensity by a factor 10. And that's why we get basically 1/10 of the luminosity. We play a few tricks here, so we don't use quite a factor of 10, but it's close. When we go lower in energy, then we become beam limited. Simply the beams get softer, so they collide with each other, and there's more damage to the beam itself when they collide. That's why we have to, again, reduce intensities, which reduces luminosities. This table here is the parameters that we need for highest luminosity. So I don't want to go through every number here. It's a large number of bunches, 1100. And what you may notice here is, for example, the emittance ratio here. That's what I talked about before. So these are the flat proton beams. So that's something very special in this machine. Another issue here is the IBS growth time. So what happens basically, you have photons in the machine, right? They are stored and they scatter off each other inside the beam all the time. And that's a heating effect. So that increases your beam size. Large beam sizes mean less luminosity because you have less density in your beam. So we have to do something, and that's why we want to cool the beam. And the electron beams here, as I said, we basically base the electron ring on the KKB factory. So these are very typical parameters for a B factory, especially a beam current of 2.5 amps, for example. So this is what gets us to a luminosity of 10 to the 34. Okay, so let's go over the various components here, the various rings. Let's start with the hadron storage ring. So we basically reuse the yellow rig ring here counterclockwise as the hadron storage ring. And what we then have to do, I told you the beam intensity, beam current is a factor 3 higher, and we have shorter bunches. So what happens is you have image currents of the beam traveling in the beam pipe. We have superconducting magnets, and the beam pipe is stainless steel. Stainless steel is not a very good conductor. So if you send these image currents through that stainless steel beam pipe, it's a resistor, it heats up. It's a superconducting magnet. Bringing heat into a superconducting magnet is basically a no-no, so you have to cool that away. If you didn't do anything, we would lose about 10 watts per meter in this machine in the beam pipe. Our cryo plant can deal with 0.5 watt per meter. So we are more than an order of magnitude beyond that limit. What we do is we insert these sleeves here in the beam pipe, in the entire pipe, 3.8 kilometers. So these sleeves are stainless steel sleeves again, but they are copper coated. So that increases the conductivity, so we don't have the problem that we heat up the beam pipe. And then there's a secondary layer of amorphous carbon on top of the copper, so that reduces what we call the secondary electron yield to avoid electron cloud. So what happens basically, your vacuum is never perfect. So your protons come along, you ionize molecules in your vacuum that are still present there, and the electrons then hit the beam pipe. They release more electrons. They get attracted by the next bunch, go through that bunch, hit the beam pipe on the other side. So you get an avalanche of electrons, and that causes an instability. So what we have to do is we have to coat this beam pipe with this amorphous carbon. And if you do that, then every electron that hits the beam pipe releases on average less than 1 electron. So you never get the avalanche, just dies out. And that's how we avoid that. Then, of course, we need new RF cavities. We need hadron cooling to create these flat bunches that I talked about before. We have to rebuild the entire interaction region here with new magnets and what we call trap cavities. I will also come to that. And we add a collimation system to keep the beam clean, to scrape away all the tails that just would cause background in the detector without doing any good to luminosity. Okay, then we have to play a few little tricks in this machine. So we have this large energy range, center of mass energy range. And the problem is we have to change, to get this center of mass energy range, we have to vary the hadron beam energy. These hadrons are relativistic, but not really very highly relativistic. So if you change the energy from 275 GeV here for photons up to down to 100 GeV, the velocity really changes. And the electron velocity, they're always at the speed of light because they have this incredibly high gamma of tens of thousands. So we have to make sure that these two beams are synchronized. So they have to have the same revolution frequency in the machine. Well, if the speed is different, then you have to cheat with the path lengths, right? You give one of them the advantage, and that's what you do here at 100 GeV when the protons are slower than the electrons, or when they are too slow, basically, you push them to an orbit that is closer to the center of the ring. So this is a beam pipe here. The center of the ring is somewhere out there off the screen. So we change the orbit by up to 20 millimeters inside the beam pipe, and that changes our path length. So 20 millimeters times 2 pi. Basically, that's 20 times, so that's 12 centimeters. So we changed the path length by 12 centimeters. That's exactly what we need to get here from this midpoint, 133 GeV. That is our nominal energy to make this symmetric here in terms of radius, down to 100 GeV. So when we go up in energy, the protons get a little faster. We have to increase their path lengths to have the same revolution frequency as the electrons. So we push them out by 20 millimeters. Okay, so that's how that works. However, you want to go lower in energy. So this is only getting you to 100 GeV in this machine. So 100 GeV versus 5 GeV electrons, that's not really anywhere near 30 GeV or so center of mass energy. So we play another trick. We have the advantage that we have two rings in rig that intersect, and we just built a bypass or shortcut here in this arc. So we have the yellow ring, and then in this arc where we nominally would be on the outside of the tunnel as shown here, this is the curved tunnel here in this section, we would be in the yellow ring. And now we use a blue arc here. We already have that thing because it's rig. Sitting here, see that? And the radius difference between the two rings is 90 centimeters. So 90 centimeters radius difference over 1/16 of the circumference, right? 2 pi is approximately 6 as well. So that changes your circumference by the same 90 centimeters. And those 90 centimeters, they just happen to be the right circumference then, or the right circumference change for 41 GeV protons. So that's just basically one energy, of course. I mean, you have a very low window there from, I don't know, 40.5 to 41.5 GeV or so, because the velocity changes very rapidly when you are at that low energy. Okay, intra-beam scattering. So I said that already before a little bit. So what's happening is you have the individual particles in your bunch there, 10 to the 9 to 10 to the 11 particles. They travel around for many, many hours. They are constantly focused in the machine by the magnet. So there is a transverse momentum that's always brought in. So they scatter off each other. They see each other. That's a heating mechanism. And that increases your emittance, your beam size, which means your luminosity just goes down the drain. So we have to do something to counteract that. And that is what we call cooling. So there are different methods for cooling. So the first one here, I apologize for this poor quality of this figure here. I never noticed that on my laptop screen. So this is conventional electron cooling. What you have here is you have the ion beam coming from the right here. That's the green arrow here. And then you merge it with a cold electron beam. That is where all the particles are nicely traveling in parallel. Basically, you even can guide them with a solenoid to really have them very calm. And then you have an energy exchange between the hot ions and the cold electrons. and that cools down the ions. So basically, you give your ions a cold bath every time they come around in this machine. So this device here is typically used in low energy machines of a few hundred MeV up to a few GeV maybe. This device here is of order 10 meters long in typical applications at these low energies. And then, of course, you have a 100-meter long ring or something. So the ions come around every time, get the cold bath. And that's how you shrink the phase space volume of the ion beam and therefore beam size. The problem here is that the cooling times here scale as energy to the 5th power. So it's very hard to get to high energy with this technology. That thing just gets super long. You need very high electron beam intensities for this cooling, right? Your bath has to be big enough if you want to cool something in a reasonable time, because the electrons, of course, get heated while they are traveling through. They get replaced all the time, but they heat up. Okay, the next method for cooling hadron beams, that's basically really how the sausage is made, is called stochastic cooling. Yes?
Does not the ion get slower when they traverse this cooling mechanism?
They get, no, their energy also gets, the energy spread gets reduced because they get the same, they get cooled longitudinally, right? They get cooled to the energy spread of the electrons, ideally, if you do that long enough. They do not get slower. Some get slower, some get faster, but that's how you shrink the energy spread. Okay, so the next method is stochastic cooling. So let's assume our beam is indeed a sausage, our bunch, and our sausage, as you can see here, it consists of these white fatty parts here. Those are my protons or heavy ions. And the red meaty part, that's my vacuum. So if I just take my sausage and I want to concentrate my fatty parts, my ions, in the center of sausage, right, along the midline here, what I can do is I measure them. I take one measurement and that only gives me the average of all the fatty parts here. I will get a very tiny deviation from 0 because it's 10 to the 9 particles or so. I can correct that, and I can correct it once, and then it's over. I can't do anything else. So ideally, what I would like to do is I would want to be able to measure the positions of all my fatty parts, all my ions simultaneously, and then correct them simultaneously. That's also impossible because it's 10 to the 9 particles, and they are just over a foot or something long sausage, so I have no chance to measure them. But what I can do is I slice my sausage. So now I slice it in all these thin slices here. So every slice doesn't have 10 to the 9 particles. It maybe is having 10,000 particles. If I measure the average position of 10,000 particles here, I see something that is not 0, that deviates from 0. So that's what I do here. I have a pickup in my machine. So this is my ring. I have a pickup that measures this slice here, measures all my fatty particles, and it measures non-zero. So then I correct it. For every slice here, I rearrange them so that the average position of all the particles in each slice is 0 again, right? So that's what I do here. This is my kicker, and now I mix. So I go around the machine until I get to the pickup again, and during this mixing, I shuffle my particles in my slices longitudinally. So I have my slices and the particles move longitudinally. So when I come around here to my pickup and I slice my bunch again, right? I slice it into the same slices at the same positions, but I have a different sample of particles in each slice than I had before. So again, I have my 10,000 particles in my slice. I measure again, and yes, the average is not 0 because these are different particles. So I can again correct this deviation from 0 with my kicker. And if I do that for a long time, then all my particles, all my white fatty particles here, they will end up along the center line of my sausage. So that's what we call cooling. That's what we want, right? The red, again, is vacuum. And vacuum, I wave my magic wand and it arranges itself around the particles whenever I do that. So in reality, the bandwidth, the cooling time is proportional to the bandwidth of my electronics, of my system here, divided by the number of particles per bunch. So for realistic electronics, I can have a bandwidth of a few gigahertz, and with 10 to the 9 particles, as we have it in RIC, for heavy ions, I get a cooling time of 30 minutes. But that also immediately tells you that for protons, it wouldn't work. For protons, we have 100 times more particles. So 30 minutes times 100, that's several days. You don't want to wait that long to cool down your beam. So that is not suitable. So we have to come up with something else. And that something else is sort of a combination of the two methods. So this is called coherent electron cooling. And what we do there, it's essentially an ultra high bandwidth stochastic cooling system. But I don't have a pickup and a kicker, and in between I have an amplifier and cables. I don't that basically transport electrons, an electron signal between the pickup and the kicker. What I do is I get rid of all the copper. Basically, I replace all that with an electron beam. So I have an electron beam that I merge with my proton beam here. And the electron beam, of course, has to also be very cold. It has to be a cold electron beam with no fluctuations practically inside. It will pick up the fluctuations in the proton beam. So they will get imprinted on the electron distribution. Then I use a free electron laser here as an amplifier. So my fluctuations get amplified, and then I merge the electrons again with the hadron beam with the right phase advance, so the right phase angle basically, so that these fluctuations now correct the fluctuations that exist in the proton beam. And if I do that again for 30 minutes or so with this high bandwidth, then I can even cool electron beams, proton beams. So because this has a bandwidth of order tens of terahertz. So that's a very different beast than what you can do in just electron hardware. Okay, so now let's come to the electron storage ring. We need that, of course, electron-ion collider. So the electron storage ring consists of 6 arcs. It has essentially the same shape as the hadron ring or as the RIC ring. So it goes clockwise, and it's here in red. We use the straight sections for the detectors, same locations as in RIC now, 6 o'clock and 8 o'clock. The RF cavities go to IR10. We have a crossover here in IR12. Instrumentation IR2, and another crossover here in IR4. So we have to have the beams, the rings have to cross over multiple times because we have to have the same circumference for electrons and hadrons. They both travel practically at the speed of light, so that's why the number of crossovers here. Okay. So one special feature of the electron ring is that we have to control emittance over this large energy range. So what electrons want to do, if you don't do anything special, is the electron beam emittance or phase space volume increases as energy squared. So if you go from 5 to 18 GeV, the emittance would change by a lot. We want a nearly constant emittance over this energy range. So we have to have several knobs basically to adjust that. One is we change the focusing in the arcs. So that is what we call the Betatron phase advance. We change that. That gets us the correct emittance at 10 and at 18 GeV. And if you go to 5 GeV, we play with our dipole. So this is a bending section here in the arc. This is a 7-meter long dipole, basically, but we split it into 3 segments, the 2 long ones with a short one in the center at 10 GeV and above. We power them uniformly, so we get this nice smooth bend here. When we go to 5 GeV, we power the center dipole in reverse, so we get this funny shape here. This sharp bend here in the center actually helps us to increase the emittance. So otherwise, from 10 GeV down to 5 GeV, the emittance would drop by a factor of 4, but this bend here gets us back to the 20 nanometers, gets us back this factor of 4, and we get our desired emittance. It also helps us reaching our beam parameter at low energies. Okay, now electron polarization, that's the part that Oleg didn't come to today, but he will talk about that tomorrow in more detail. So the physics program requires bunches with both spin up and spin down in the arcs. That means up and down stored simultaneously in the electron storage ring. So there is a process that you will learn about tomorrow, so-called of turn-off self-polarization that's related to synchrotron radiation that would produce over time by self-polarization bunches that are polarized anti-parallel to the main dipole field. There are a few problems with that. One, of course, is you would end up with all the bunches in the same direction. You don't want that, so that violates this here that I want to have spin up and spin down simultaneously. The other issue with that is that it takes too long. At 18 GeV, the self-polarization time is 30 minutes. That's okay. The problem is it scales as gamma to the 5th power. So if you go to 10 GeV, it's several hours. If you get to 5 GeV, just forget about it. It's days. So that self-polarization is out. The only way to get these arbitrary spin patterns in this machine is by actually injecting bunches with the desired spin orientation at full collision energy. So at 18 GeV, 10 GeV, 5 GeV. And what will happen then is, of course, the so-called of turn-off effect that normally helps us to achieve high polarization, though only one direction, will then again do its same thing. It will slowly reorient all the spins in the same direction. They will all start flipping because there's one preferred direction, and that is the one anti-parallel to the main dipole field. And that, of course, has a time constant of 30 minutes, for example, at 18 GeV. So after 30 minutes, there would be noticeable polarization loss or polarization loss in one spin direction. So I would lose that. There are other effects that make it even worse, that cause polarization loss apart from so-called of turn-off. So the only way to overcome this is by replacing the bunches at a rate that is faster than the so-called of turn-off time and also the spin diffusion time constant. So this is how we do that. This is how it looks. This picture here, this is just an example basically with these parameters. So I assume that if I didn't do anything, then so-called of turn-off together with depolarizing effects would give me 30% polarization. So that's the equilibrium polarization of my machine, right? And I optimize that because that will help me, but here I use conservative number just to show that even then it would work. So then I assume that I get 85% polarized electron bunches from my injector, yeah, positive or negative 85%. I inject them here, and then of course they will decay. The polarization will decay over time towards this 30% level here, the equilibrium polarization. Yes.
Why did the spin up and spin down need to be held simultaneously?
That is for the detector people basically to reduce systematic effects of the detector. You look for asymmetries in your physics, right? And if you only have spin up now and in the next store, for example, 12 hours later, so you have spin down, then all you could see is maybe a day-night effect. It's not has nothing to do with spin, right? You flip it every 12 hours and there are things like day, night that change also at the same rate, and you would fool yourself.
Thank
you. So I'm injecting 85%. It decays here towards 30% over 30 minutes here at 18 GeV. But what I do is once it reaches about 70%, I kick that particular bunch out and replace it with a new one. So from my 70%, I go back to 85. So I get this sawtooth behavior. This is what happens for every single bunch in the machine. So my time average polarization is 80%, and my ensemble average polarization is also 80% because I go around the fill, around my 1160 bunches, one by one, and replace one bunch per second. What you also see here is if I inject bunches with negative 85%, I have to replace them faster. Reason is simply that my positive 30% equilibrium polarization is further away. So I get a steeper slope here in my depolarization, and that's why I have to get faster. This is the electron injector system. It's a cartoon that shows how we do that, where the electrons are coming from. So I have a 750 MeV Linac. It's a copper Linac. It's standard technology. It runs at 30 hertz repetition rate. And I go into the bar. It's always good to go to the bar, even at daytime. So that's our beam or bunch accumulator ring. So I merge these 30 bunches or 28 bunches here that each have 1 nanocoulomb into a single bunch, into a single 28 nanocoulomb bunch, because that's what I want in the electron storage ring. Send it into the RCS, the rapid cycling synchrotron. That's a pretty big machine, 1.4 kilometers circumference. And from there, I go into the ESR. So I swap out these bunches here. I kick out a bunch out of the ESR onto a beam dump and replace it with a fresh bunch from the RCS. This is how the layout actually looks like in the cartoon. So this is the 4 o'clock area of rig or of the EIC. And then we attach this new ring here. It's a new tunnel, 1.4 kilometers for the RCS. The RCS is a special design in terms of optics, of magnet layout. I don't want to go into that detail here. That would get us too far. Normally, if you accelerate electrons or even polarized protons in a regular machine, you would lose polarization because of these spin resonances, these depolarizing resonances that Oleg was talking about a little bit. You can avoid that by having a special optics layout, a special magnet layout in the machine that pushes these resonances to energies that are outside your operating range. So if I inject here at 750 MeV and I go up to 18 GeV and I manage to push my lowest depolarizing resonances, the first one below 750 MeV, the next one is at, let's say, 20 GeV, then during its entire ramp, this machine never encounters these depolarizing resonances. So polarization is preserved, and I can get into the ESR, the electron storage ring with polarized electron beams. Okay, let's come to the interaction region. So this is always something where people it's a little bit of a wake-up call in many cases. So you know that luminosity is proportional to 1 over the spot size of the beams, right? That's your density of your beam there. That means a smaller spot size at the interaction point means more luminosity. However, what is also true is, and this is related to this whole phase space volume stuff, emittance stuff that I'm talking about, the product of beam size, RMS beam size, and RMS beam divergence at the IP is constant. That's a property of the beam, has nothing to do with the machine. So for a given beam with a fixed product, with a fixed emittance, if I increase my focusing to a smaller IP beam size to get more luminosity, I get larger divergence, right? This angular divergence of the beam gets larger, and I have to place magnets here somewhere outside my detector that actually focus my beam to this tiny beam size. So these magnets have to have enough aperture to accommodate the beam. The smaller I make the beam size here, the larger the beam gets here in the magnet. And there are technical limitations. So these are quadrupole magnets. I can make them superconducting. But at some point, if I need a gradient magnet here, I need a magnet with a fixed gradient. That means if I increase the aperture, then my magnetic field here at the aperture here or in the coils has to increase for a given gradient. And I can only go to whatever, 5, 6, 7 Tesla up here, and that's it. So that limits my gradient, and that means I have to limit the beam size in my magnet, and that eventually then limits my my luminosity because it limits the beam size at the interaction point. What this also means is that I want to push my focusing elements for both beams, for electrons and protons, as close as possible to the interaction point, of course, because this angle here is fixed. That's my divergence. But if I push my magnet closer to it, it can be smaller because my beam is smaller. But there are limitations because the detector people don't want me to put my magnets where I would like to put them. So what can we do there? How can I get the focusing elements for both beams as close as possible to the interaction point? So one challenge is the beam energies for the electrons and the hadrons are vastly different in EIC by an order of magnitude or so. So they cannot share focusing elements. If I had the electron focusing elements first and have them shared by the hadrons would barely care because they are just too stiff, the energy is too high. So that wouldn't help me with the hadrons. If I put the hadron focusing elements first and wanted the electrons to share them, the electrons would just get over-focused because those magnets would be too strong. So what do I have to do? Well, I have to separate my magnets before I get into the focusing elements. And I want to have these focusing elements as close as possible to the interaction point. So I could introduce a separator dipole that bends the electrons away from the protons or from the hadrons. The issue there is, of course, if I bend the electrons away, I get synchrotron radiation. It's a accelerated charge. So I get synchrotron radiation. That is a huge fan of synchrotron radiation, pretty hard photons that would have to travel through the detector beam pipe. That means my detector beam pipe has to have a large aperture. That's, again, not what the detector people want. They want to be close to the beam. They don't want to have to stay half a meter away from the beam just because stupid photons have to go through there. So that is not the preferred solution. So the best solution is actually to collide at a crossing angle, right? I cross the beams at a small enough angle that I can put my focusing elements for electrons and protons side by side outside the detector on both ends. But of course, there's also an issue with that. So there's an issue if I collide at an angle with the luminosity. So in a head-on collision, that's shown here, I have two bunches here. I show equal bunches here. So assume this is rigged. The electron-ion collider, it's different. The bunch length for the electrons is shorter than for hadrons, but that doesn't matter for this argument here. So every particle that is in one bunch here, let's say there's a particle here at the head of the green bunch, has in principle a chance to collide with every particle in the blue bunch. If I now collide at a crossing angle and I look really at the beam sizes there, the length and the transverse size of the bunches, then now I'm colliding these two needles here at a crossing angle. So they move in this direction and in this direction, and the overlap of the bunches is much smaller. So a particle that's sitting here in this slice here, in this transverse slice of the yellow bunch, has only a chance to collide with the particles in this corresponding slide of the blue bunch. It can't collide with the particle that's here because they just arrive too late. They don't get to the crossing point at the same time. If I go through the numbers here, then it turns out that a 25 milliradian crossing angle, which is actually what I want for my electron-ion collider, only a slice that is about 4 millimeter thick has actually a chance to collide with a 6 centimeter long oncoming proton bunch. So that's a huge reduction in luminosity. This is just here, this simple numbers. In reality, it's more like a factor 100 that we lose in luminosity. So you have to do something to get that back. So I want the crossing angle, but I don't want to lose luminosity. So what can I do? Well, there's something that we call crab crossing, and I wish I had the same animation for just the regular crossing without the crab crossing, instead of having these stupid pictures on the previous slide. So what happens here? So the bunches come here from, it's again equal bunch lengths, but it doesn't matter, from the upper left and the upper right. And then I have cavities here that kick the head and the tail of the bunches in the transverse direction. And when they tumble around, there are still magnets here. And when they arrive at the interaction point, they are lined up with each other. So now I have perfect overlap of the two bunches in the interaction point, and I get my luminosity back. So this is the ideal situation here of head-on collision in combination with a crossing angle that allows me to have my magnets. Yes.
I guess this goes back just a couple slides, because this is a solution to the angling, and the angling was a solution because you needed to focus the two beams separately. And I could see that focusing an electron beam would be too, like trying to do it the same way to the hadrons wouldn't focus them enough. But why, I guess, what's the issue with over focusing? Like if you were to focus, the way you focus hadrons, if you were to apply that to the electrons, you said they would be over focused. But I guess I don't really know why that's a problem.
Because then you have the wrong focal length, right? You want to have your focus at the same location. You want it to be 5 meters after your magnet, after your length, right? If you're over focused, then it's 1 meter after your length, and then it gets large. Once you get to the 5 meter point where you want to collide, you have a huge beam size. So you have to have the same focus location.
Okay, thank you.
Yes.
So after you rotate the bunches in order to maximize the overlap,
Yes.
is it very difficult to recover? Or I guess that introduces some effects in the final state, right?
So
Because it's introducing some sort of rotation.
yes, and I have to undo it on the other side.
You have to correct, right?
Right. I mean, that's why I come here. They are aligned with the orbit, right? Then they get kicked, they tumble around, and here that is then compensated again. what you have to do in your analysis for your detector is you have to take into account the fact that these are transversely moving as they collide, right? They overlap, and there is this transverse motion there. So that's a timing issue in the end, but that can be done. All right, so the world was just perfect, but it's not, because nobody's perfect. The problem is these crab cavities, that's a sinusoidal RF field. And that, of course, has a limited bandwidth, not an infinite bandwidth. And that bandwidth is the wavelength, I mean. And that wavelength is larger, obviously, than the bunch length, but it's not a lot larger. So there's really an effect. You see the nonlinearity. So the beam arrives at the zero crossing of your sine wave. But of course, if you go away from your zero crossing, then yes, first it's linear, and then at some point you see it's not linear. And that is shown here. So the blue bunch here, these are my protons. As they align with the electrons are short, so they don't see it. And you see that the head and tail are distorted of this thing here. That is the effect of the finite wavelength of these crab cavities. So you get this S shape here. And that results in nasty beam dynamics effects if we don't do anything about it. What we have to do is actually we introduce a second harmonic crab cavity to linearize this part here, and that works. So we need two sets of crab cavities for the hadrons. For the electrons, we only need one set because the bunch is only 1 centimeter long. The hadrons are 6 centimeters long, RMS. And so we need 197 megahertz crab cavities. And then the second harmonic, 394 megahertz harmonics, crab cavities. The frequency is given, of course, by the bunch repetition frequency. You want this frequency as low as possible. And actually 197 megahertz is practically the lowest you can go, because these are superconducting cavities. They are built of niobium, and the commercially available niobium sheets have a maximum size. You can't make this thing bigger currently because you just can't get the material. And of course, it is a beast. It's a 197 megahertz cavity. That's a huge thing. This is how it looks like. Don't want to go into too much detail here, but just to show you a cavity. So you have here these are two cavities in one cryo module, and you get a transverse field here to kick the head and the tail of the bunches to get this crab cavity effect, this rotating effect. They are being built and tested at JLab. So here you see a few of the niobium parts that have been manufactured there for these cavities. All right, so finally, let's come to the actual layout of the EIC interaction region. So we want a small, what we call beta function, beta star. That's a small, is related to the small spot size at the interaction point. To get to high luminosity, we have to make sure that these very strong magnets here don't screw up basically our optics in this machine. You get chromatic effects, so you get different focusing strengths depending on the actual energy of your particle that goes through the magnet. And you always have a momentum spread or energy spread, so that's unavoidable. And of course, there are these limited sizes for the final focus quadrupole, so we have to really push that. There are physics requirements that drive this interaction region layout here. So the requirement is a large detector acceptance, and then forward spectrometer for all the stuff that come on. For all the stuff that comes down the beamline from the IP and travels together with the or in the direction of the hadrons. And these boxes here that you see, these are all the individual magnets that we need, and they indicate the apertures of the magnet. So this is not the outside of the magnet, that's the inside of the beam pipe. The yellow part here, that's neutral particles, neutrons that hit the zero-degree calorimeter. And then we have Roman pots here along the beam pipe to catch any particles with a transverse momentum of up to 1.3 GeV/c. The electrons are coming from the upper right. So we have the focusing elements here, and a focusing element, of course, does essentially the same as a dipole. It generates synchrotron radiation, photons. So we have this photon fan here or cone that has to pass through the central detector, has to pass through the magnets on the downstream side, because you don't want these photons to backscatter into the detector. And then finally, we can absorb them. We have beta-Heitler photons that are coming. These are basically Bremsstrahlung photons generated in the interaction of the protons and the electrons. They are our luminosity signal, because that process can be calculated to very high precision, basically the cross-section for that. So that's the luminosity signal. So we collect, or we measure these photons here. They get converted into electron-positron pairs because it's a very high energy photon that comes out there. So that's the luminosity signal. And so basically, this is a multi-stage separation of beams and particles and photons. So we have to separate the hadrons from the electrons. That's the easy part. That's the crossing angle. Then we separate the protons or any charged particles on the forward side from the neutral particles by introducing a dipole magnet here. For the electrons, it's similar. We separate the beam from the photons here also with a dipole magnet, and the hard beta-Heitlers from the synchrotron radiation photons by a window here. So the synchrotron radiation photons cannot penetrate that window, while the hard beta-Heitlers can. This is just a prototype, a cross-section of one of these superconducting magnets that we use in the interaction region. So in superconducting magnet, the field is dominated by the arrangement of the conductor of the superconducting coils. There is no steel yoke that shapes your field. So this is a dipole, right? You can see that here, vertical field lines. And what you have to achieve is a cosine theta distribution of your currents in these conductors to get this dipole. But the challenge is that your conductor, your physical conductor, is basically these little keystones that you have to arrange, and you have to leave gaps and so on. You can also have a second layer or a third layer in some cases to approximate this cosine theta distribution of your current to get as homogeneous as possible dipole field here in the center of the magnet. So that is one of the main challenges in superconducting magnet design. Okay, so we built even a prototype of this magnet. That's our most challenging magnet. It's a big piece. It has 30 centimeters aperture. And this is what is happening at Brookhaven at superconducting magnet division. Here you see basically the view of the coils. So these are the coils, how they are arranged on the beam pipe. And the other challenge here is to get the ends right here, so you don't introduce any nasty field components at the ends. All right, another type of magnet that we are using or planning to use in the electron-ion collider is tapered magnets. So you see that we have lots of magnets here that basically have the same function, and especially here, the Q1 APF, Q1 BPF, for example, they have different apertures to get all the particles through the beam and the neutrons and the scattered particles, and also here for this dipole here, B1 PF, B1 APF. Similar thing, it's basically the same magnet, but we have to split it up if you don't do anything special because of the different apertures that we need. Come on. Okay, so the idea here is to replace these two quadrupoles here that we have with two different apertures and essentially the same, or having the same function with a single magnet. Does this work? Yes, with a single magnet. So instead of having these two purple boxes here, we have now a tapered magnet that has the same function as these two separate. It reduces the number of magnets that we have. It's always good for manufacturing. It also has the advantage that the center of gravity, or the focal center of this lens here, moves closer to the left, because it moves to the point where I have smaller aperture, which is good. That is closer to my detector. So that brings my magnet actually closer to the interaction point, which is always good, as I explained before. So this is how this is implemented. I don't want to go into too much detail here, but here, down here, you see the gradient as it increases as when you get closer to the interaction point because of the smaller diameter, the smaller aperture of this magnet. So that's a good thing. That pushes my lens center closer. Here, I don't want to go over this in too much detail. This is how this magnet is built. So this is a different technology of building a magnet. Instead of having these keystone conductors that have to be placed very carefully, this is a technology that has been pioneered at Brookhaven 30 years ago or something. These are superconducting wires. They are round, and they get directly glued onto the stainless steel V pipe. So you glue them on. We even have movies. I couldn't find one. You glue them on here, then you cover the whole thing in epoxy, and then you move on to the next layer. And the advantage is that you typically need 10 or 12 layers of these magnets. And after each layer, when you finish it, you measure the field quality of the magnet and you correct for any errors in the field quality in the next layer. So you can build very high field quality magnets with this technology, which is pretty straightforward if you know how to do it, because you just glue on conductor. Okay, quickly, spin rotators is another type of magnets that we have. So the hadron spin rotators are based on helical dipoles. These are the same spin rotators that we have in REC. So they rotate the proton spins from the vertical to the longitudinal direction around the interaction point and then back to vertical. You see here basically these grooves in the beam pipe. So that's where the conductor is. That's what makes this helical dipole, this twisted dipole. For the electrons, we have a different type of spin rotator. It's based on solenoids. So the spins are coming out of the arc vertical. Then we send them through a solenoid magnet, a longitudinal magnetic field. They precess around the magnetic field lines, so they get rotated from vertical into the radial position, pointing outwards or inwards radially. And after that, so we have to set the field, of course, to the right value. After that, they go through a set of dipole magnets, which just the right bending angle to rotate these spins from radial to longitudinal position at the interaction point. And then on the other side of the detector, we do the whole thing in reverse to be back into the vertical direction in the arcs again. Okay, I'm coming to my end here. So this is the timeline of the EIC project. That's what everybody is always asking us about. So we are here where this star is. So there are these milestones, critical decisions by the Department of Energy. So CD0 is approved mission need. That basically means, yeah, okay, it would be a great idea to build an electron-ion collider somewhere. Then there is CD1, critical decision 1, where alternative selections are approved and the cost range is approved. So they look at different ways how to realize this machine. So that's where we are. So Brookhaven has been selected as the site in CD0. The alternative selection was we went through and we had the cost range approved. So that was in 2021. We are now gearing up for CD2. That's approved performance baseline. So that's really when it is approved what exactly we will build. And CD3, that means start of construction. So that's really when we can cut metal and really build this machine. Finally, CD4, that is when operation starts. So when the machine has been turned on, has demonstrated what they call key performance parameters that really show, yes, this machine works. The key performance parameters are not ultimate performance, so you don't get 10 to the 34 luminosity at that point. That takes longer. The Department of Energy wants to finish a project. They just want to make sure, yeah, okay, it works. No major bugs, so this looks good. So that's the end of the project, and that starts then operation. And yeah, there we are envisioning 2034. Sounds like a long time, 9 years. But I'm always puzzled that when we started the design of the Electron-Ion Collider in earnest, that was in 2015. So that was 10 years ago. So we're already halfway there if I go back to 2015. So time flies. Okay, now finally my summary. So the EIC is a very complex, challenging machine. I hope I got that message across. It's much more complex than the LHC. High luminosity, polarized beams, crab crossing, beam cooling. We have this large energy range instead of sitting just at one fixed energy like the B factories, flat hadron beams, something nobody has done before, and so on and so on. There are so many things there. What's important is the machine, the design meets the requirements that are laid out in this mission needs statement. When DOE said, yes, somebody should build this. We made a couple of crucial design changes, notably on the RCS. Let's maybe I have 5 minutes for that. So the RCS was originally planned to be inside Collider Tunnel. He said, oh, we have this beautiful tunnel there, 3.8 kilometers, and yeah, we thought we had space in the tunnel. But what was really the issue is we had a 400 MeV LINAC that was supposed to feed this RCS, this 3.8 kilometer RCS. So that meant that our dipole fields would be of order 50 Gauss only. So 50 Gauss is a low field. And at some point, our magnet designers came and they said, well, I have a problem. You want the field quality for your dipoles or field fluctuation. Think of field fluctuation in your dipole of better than 10 to -3. So now you put a 50 Gauss dipole somewhere, and it is in an environment where you have an Earth magnetic field of half a Gauss. So that's already a percent. So why do you even care about what I give you? Because you have this nasty magnetic field from the Earth that is 10 times higher than what you are asking me. Something doesn't make sense. So we thought about that. So the first step was to increase the injection energy from 400 MeV to 3 GeV. That would have fixed it. So then we would have gotten to that our fields would have increased by a factor of 10 roughly. So we would have had 500 Gauss instead of 50. So that would be 1,000 times the Earth magnetic field. That would have worked. However, then we looked a little closer and we said, well, maybe our tunnel is not as large as we really thought. So we did layouts there in CAD programs. And the main issue was this arc here where we have to leave the blue arc in there. So we had then 2 ring arcs side by side, the electron storage ring plus the RCS all next to each other. And nobody really knew how to install it. It looked good on pictures if you just assumed it magically appeared there. But moving magnets or any other equipment through the tunnel and installing them in a certain place seemed to be possible. So that's when we decided, okay, this thing has to get out there. And that's why we then changed it to having an RCS outside in a separate tunnel. Okay, so the design is well underway. As I told you, for 10 years we are working on it, preparing for this CD2, CD3. So that's approval of baseline and start of construction when RIG ends. So we are shooting for next year in June for CD2. And CD4 is planned for 2034. Of course, that assumes that we get the funding that we need. Any reduced funding delays things, and delays also cost money. So the OE should understand it doesn't get cheaper if they delay things. So hopefully they will give us the money that we need. Thank you.
Thank you.
I don't know if I missed it when you were explaining it, but there was a section on beam cooling for hadron beams because, you know, you have this collimated beam and they're all going to be interacting with each other. Does the same issue not happen for electrons?
No, electrons have a natural cooling effect, and that's synchrotron radiation. That's the nice thing. So we are. So just consider the vertical plane, right? You have a particle, and that particle comes through here. There's my electron, and now it emits a photon. The photon is emitted in the direction of the particle. So if you send a photon here, then it reduces the momentum of the particle, both the longitudinal and the transverse. Right? So now you reduce your transverse momentum of the particle, it gets back to the accelerating section. The accelerating section restores your longitudinal momentum, but not your transverse, and that cools it down. So in the vertical plane, that's easy to explain. In the horizontal plane, of course, there are heating effects due to synchrotron radiation because you always emit photons in the dipoles. But in the vertical plane, it's very simple.
So CD4 is when runs start?
Yes, that's the end of the project.
The end of the program. And like how after how long after the runs start can we actually like take data and analyze data?
That starts essentially immediately, but of course you don't get the ultimate performance.
Say 2034. What is going to be the first run? What's energy combinations? Not really.
Oh, the energy. Yeah. Okay, energy combinations. There we have to go back to by radial shifting here. Okay, so what we would like to do is to start basically without having to shift the radius in the hadron ring in our first run, because yes, we have to go close to the wall at 100 GeV, right? With heavy ions, basically, there is not much up here. This is only protons that could do it. So we could start, for example, with 130 GeV protons. 150 would be the same practically for us in the center. If we started with protons, however, I think nobody is interested in unpolarized protons, and it may take us a while to get the polarization back again after rebuilding this hadron ring from ring into the EIC hadron ring. So we looked at some heavy ion species. Basically, we have a different figure for this. It's the same curve, but it's a different scale that has different species here. And so there are certain species that would be preferred where we have a lower A/Z ratio. So A/Z for gold is 2.5. If we get a bit closer to 2, it would also help us. So the most challenging beam, basically, in that sense, is gold, or any heavy ions, gold or uranium, because we have to run at 100 GeV for gold. We can't get higher. Okay, it's 110. We can't get higher. The magnets can't do it. So we are down here. So the magnets are at the limit, but on the other hand, we also at the limit of the aperture. So we would not want to start there. We want to have something that in this figure here is closer to the center, so we don't have to run something that is challenging in the beginning.
For people who study nuclear, yes, first.
Okay.
And we were giving talks about the EIC. We would always say things from the white paper saying that the EIC is the center of mass energy from 20 to 100 GeV, upgradable to 140.
Yeah.
True that now it's from 100 to 120 to 140, no upgrades.
It's 29 to 140.
29 to 120.
29 is 41 GeV on 5.
I see.
We can go below 5 GeV in the electrons, but unpolarized. And I think there's no interest in that. And the the increase there, this upgrade from 100 to 140 GeV, that is, yeah, it has reasons because of the competition with JLab at that time.
Okay.
So the JLab, basically the site is limited, and their approach to get to 100 GeV center of mass energy, they needed 8 Tesla magnets, which is LHC level, right? And if you then want to get to 140 GeV, you have to double that, 16 Tesla. Yes, you can only sell that as an upgrade. Nobody would ever believe that. If you said, I build a machine tomorrow with 16 Tesla magnets, that would not fly, I think.
Other questions or comments? Ready for lunch, so let's thank Christoph. Let's try to be back at 1:30.